So we have to start with what are objects of study, which are complex vector bundles. And so that means that they're fiber bundles whose fiber is a complex vector space. That means you have a scalar multiplication, not just by the real numbers, but by the complex numbers. More generally, if you think about the overlaps, you're looking at not just C-linear maps between the trivializations, but not just R-linear, but C-linear maps between the trivializations. So you, in the language that we were just developing, that means that your structure group restricts to, or just is GLN-C inside, GLN2N-R, which is in self, if we're thinking about bundles very generally, inside the homeomorphisms of R2N. So you're looking at a smaller group that's the structure of the isomorphisms that we're allowing. Alternately, you can, if you put a Hermitian metric on everything, and this is one of many times where I'll say it works as we did in the real case, but with the complex version, then you can substitute UN inside of O2N, the unitary group. So that's a nice compact model. A good example is complex line bundles are exactly oriented rank 2 real bundles, oriented plane bundles. And you can, well, you'll see the connection between complex multiplication and orientation again in a second, but in this principal bundle point of view, structure group point of view, that's because U1 is isomorphic to the positive determinant component of O2, SO2. In general, let me define a little bit of terminology. We'll call a weakly complex manifold is one whose tangent bundle is complex. In other words, can be given a complex structure. And I'll emphasize complex topological bundle structure. It's complex bundle structure. So if you've done some algebraic geometry, smooth varieties are complex in a very strong sense. Sort of there's an analytic aspect to it. This is much weaker. This just says that the bundle, there's a way I can consistently multiply by I on the bundle. So in general, but there is some strength to it because a complex vector bundle is, I'll say, canonically oriented. So not only orientable, but there's a consistent way to orient namely for any so you need this choice of equivalence class of bases. And what you can do is in your local charts, or however you want to think about it, for a complex vector space V, take any basis, V1, say, to Vn over C, and over R, you take V1 and then you multiply it by I, and V2 and you multiply it by I. And this forms a real basis. And the claim is that all of these real bases sit in the same orientation class, so to speak, the same equivalence class with respect to orientation. And you can see that in, and this is a well-defined orientation class. Sort of explicitly, I mean, the main thing that gets tricky in orientations is taking a basis, and if you swap two basis vectors, then of course you're no longer, do you have an oriented basis? But here, if I swap, say, V1 and V2, well, under this construction, I'm actually swapping four vectors, V2, I, V2, V1, I, V1, and you can check that that's an even permutation. In other words, there's actually four swaps, if you will. 1, 2, 3, 4. And so this is gives an orient. This is still in that orientation class, so that should convince you. But then the main thing is that that because any two such are related by GL and C, which is path connected. And because the choice of orientation is a continuous map into a discrete, namely 2-point space, if I have a path, then that along that path it's got to be constant. So so that's gonna mean in particular that we get to leave the mod 2 world, which you might find exciting because we're going to be able to see odd torsion and feel like things are more less flimsy perhaps. But this is sort of the best of the world over the integers, because actually tracking orientations is a pain, but for complex kinds of objects, and again, weakly complex is really what we should be thinking here. Orientations are there, and much easier to track because of this basic observation that complex bases complete in a canonical way. I mean, I guess not entirely canonical. You could put all the I's later, but in any case, there's a wonderful, consistent way to do it. Okay, so let's remember that. So let's recall that our tome. So we're going to do churn classes, and we're going to see that basically the theory is essentially the same as for Stiefel-Whitney classes. Recall that tome cochains over Z require, so we needed for the Euler class, require that our manifolds which map to M factor through some bundle, and then we have a normal bundle here, and we have a co-orientation. It is an orientation well, it's a choice of such map. It's a factorization plus an orientation of this normal bundle. And so, yeah, so we're going to use tone cochains once again to define now what are called Chern classes. So, yeah, so given a complex vector bundle, and now I'll often, you know, before I was saying V to E to Ev to just sort of emphasize that the fiber isn't sort of canonically Rn. Now I might actually lean towards the other standard notation, just because then for free, we're emphasizing this is Cn, not R2n, so we've got a complex structure. The class Cn is just the is going to be the Euler class again. So that's in H2n of E or M. It's represented in H2n of E. It's the tone cohomology class of 0, the 0 section inside of E. So that's as before, and here this is co-oriented in E if you want, and so just we don't even need the factorization E, so to speak. So that's as it was, but we then define lower Chern classes to be the tone cohomology class of, well, we're just going to basically repeat our definition. We're going to repeat a lot today. If you go back to lecture 17, I think this is lecture 20, you could follow what we did there, and we're going to sort of see it play out once again. So we'll kind of know this fundamental theorem really well. So I've got this dep dependent I+1 vectors hat, so sort of blow up, living over I+1 copies of E. It really sits then, its image are the dependent collections of vectors. And what is this? Let's recall that, well, if I have I+1 dependent things, then they sit inside some I-plane in E. And then to take a, and here's now where I'll try to remember to put C's everywhere for complex. Now I'm looking at the I-planes which are complex I dimensions, so real 2I dimensions inside of real 2n dimensions, but complex I dimensions subspaces in E. And then to take a point, 1 point on it would be the total space of that tautological bundle. But then I want I+1 points. And then this sits over E plus E plus E, because I just remember those points in the image, again, because I've forced things to be sitting inside an I dimensional subspace. This should be just I. Then those I+1 points are dependent. So, so this is itself a bundle, if you will, over the Grassmannian. And in fact, in order to co-orient it, we can, so to co-orient this, what we can do is, well, we can embed GRI complex. Let's remember, I'll try to put our complexes of E, so the I-dimensional subspaces of E that sits over M. And it, by sort of Whitney embedding, we can get that it sits inside some Euclidean space. We can also, one way to topologize the Grassmannian that I don't think I mentioned before, an I-dimensional subspace, I can look at the sort of the unitary projection onto it. And so this gives you an embedding in the endomorphisms of E. So in fact, a subspace gives you an idempotent linear map because you project onto the subspace, and that composed with itself is itself. So you embed that inside some Euclidean space, but really we could just or more generally just some R in, and or let's just make it a Cn, because what we're going to do is then the and so that means that gamma I is inside of this Cn, if I think of that as a real bundle over M plus E plus, well, each gamma I is sits in there, and so I can make a bundle which is big enough. But the point is that that my factorization now is, well, so here's some exercises to leave to you. So in general, if V is a complex vector space, then the space of lines in V are more generally the space of, and again, we can put a C here or not, or I-dimensional complex subspaces of V. Again, if you understand that V is complex and have a convention that by I-dimensional subspace, I mean the complex ones. Anyways, these are, again, what we would call weakly complex. And by the way, that just means there is a J from the tangent bundle, or and this will be true for any a way to multiply by I. So J squared is -1. So so they're weakly complex. This is another, this condition on this J existing is another way to say that any real two-dimensional bundle is complex in our sort of weaker topological sense. And then more generally, if right, so we more generally, the idea, well, we're over some M. M isn't necessarily itself weakly complex, but if we can embed in let's see, we can well, in a way so that the normal bundle is complex. So that really means that we are going to think about our embeddings really as I sort of said, we want to think about the Grassmannian itself as embedded in some complex object. I gave the endomorphisms as one way to do that. And then the M, we're not going to have any sort of normal directions there. So that's the idea. Okay, so so then if we then have this co-orientation, right, now we have our definition of Chern classes. They are exactly where, then if I'm thinking in the base, where I+1 sections become dependent. And so then a lot of what we did for Stiefel-Whitney classes remarkably also continues with some differences. The main one being that we're now working over the integers because we have these orientations, these co-orientations. Let's see, what do I want to say? So let's think about the different axioms. So Ci Rnh2I when you count dimensions, and Ci equals 0 if I is not between 0 and inclusively. C0 is the identity. Because you end up just sort of seeing all of E or something like that in that case. Ci are natural. That is Ci F upper star E is F upper star Ci of E. This is pretty immediate because we can use, we can also pull back the section, and we thus are pulling back sort of all the data that makes the tone cohomology class. And then you have, you know, the tough axiom, Whitney sum. And for this, we, this will again will be we need the classification theorem that any tame bundle is pulled back from Grassmannian. We need the cell structure on Grassmannians. And here's the here's one wonderful difference. These are only even dimensional cells, and that implies that the differential is 0, and that's something we proved. I gave about 3 different arguments in the real case, but here just the admittedly difficult work. You know, you have to roll up your sleeves to get this, get the cell structure, but that work alone, without any further analysis, gives the additive structure of cohomology itself. And then finally, we would have a direct calculation of the total total Chern class of a product of, well, direct sum of n copies of the tautological line bundle that's sitting over CP infinity as just the product of 1 plus xi again, where xi is now a generator xi is the generator of degree 2 in CP infinity. Once again, that generator, we now will want everything to be, we're going to choose our orientation on S2 as CP1, which means, once again, there's a canonical basis now. As a complex object, there's quote unquote only one orientation of S2 that we're really considering. The other one would be the conjugate orientation, if you will. So anyways, this is inside this polynomial algebra. As we said, xi is an H2, so this is the cohomology of a product of CP infinities, or BU1s is another way to say it. So that direct calculation, if you go through what we do there, it translates. You just replace the all these vector spaces with their real bases, and we gave we found sections by taking diagonal copies of our standard basis vectors, because the bundles are embedded in trivial bundles, and those formulas still work. And yeah, and the point is that, for example, the homology of complex projective spaces are still given by classes. We can even call them BI in degree 2i, and we're going to go through this calculation a little more carefully, but in a slightly different matter. We're going to understand a little bit better this relationship between complex projective spaces and our Grassmannians. But in any case, the calculation stands, and all three of these still give the Whitney sum formula. Use the classification theorem to reduce it to and as well as the cell structure on Grassmannians tells you that the map from the Grassmannian of n-planes in R infinity C infinity injects into the cohomology of a product of CP infinities. Once again, as symmetric polynomials. Now this is over the integers and not Z mod 2. So those two facts together allow you to appeal to this direct calculation, and because that map is injective, deduce the general case from the Whitney sum formula for line bundles. So the other thing this calculation is a generalization of sort of what we would call axiom 4, and that is our sort of normalization. It's kind of like the dimension axiom that homology is not trivial or something like that. In this case, it's that gamma 1 C over P1, of C2, say, lines in C2, so CP1, that this has C1 is the generator, because again, we've chosen a way to orient CP1, which is S2, through this weakly complex structure. This is the generator of h upper 2. So this direct calculation also gives us that. And this bundle here is so it's the analog of the Mobius bundle, right? And we've found the Mobius bundle was a great example to appeal to in a number of cases, and gave us some intuition. And here it's even more the case that this is a bundle worth studying. And so next lecture, I'm going to devote all the time to just this bundle. It's the Hopf bundle is the way I like to refer to it. So we're going to just talk about this little piece of both a direct calculation, but I care less about that than the geometry of this particular bundle that underlies the structure of Chern classes. Let me say another thing to do is, and I'll give this also as an exercise. Compare this definition. Compare the the dep hat definition of Cn minus I with the Milner and Stasheff. I think it's page 157 or 137. Can't read my writing. With the Milner and Stasheff definition. I'll sort of talk through it. What they do is, given any bundle, you look at, I like to do this with the sphere bundles, you look at unit spheres. So if we're complex, we want to make that unitary. So picture an S1 bundle inside a complex line bundle, or an S3 bundle inside a complex plane bundle. And then you can, for any vector, so that bundle is going to be a new base of a bundle where you now look at, so every point in that bundle has a line going through it, and I can look at the orthogonal, or well, the unitary complement of that line, Hermitian complement, I forget, or I can look at the quotient of my original bundle by that line. And you then, for example, look at the Euler class of that, and that ends up being Cn minus 1. And you can play that game again. Now you have a bundle over a base, and you can look at the sphere bundle in that bundle each time the dimension goes down by 1. And if the basic idea is that definition is equivalent to ours, because this basically says in the first case that two vectors are dependent if and only if one becomes 0 in the quotient by the other. Just good to go through some of this, but for that definition to work, there's a bit of work in the Giesen sequence. It's not so bad, but you do have to develop the Giesen sequence. And this definition works for Stiefel-Whitney classes as well. Milner and Stasheff give it as an exercise to reduce to show that these that you can use the Giesen sequence to construct Stiefel-Whitney classes which satisfy the 4 axioms. Again, I'm not sure. It's a good question how the Whitney sum formula goes in that setting. In any case, it's worth a comparison, because it's also part of thinking more geometrically is sometimes connecting with arguments that are inspired by that geometry, but maybe a bit sort of different and formal. Okay, so we're gonna stop there, and again, next time is Hopf bundle day.